Okay, so we're going to start looking now at how we digitize images. So a lot of the stuff we've seen so far was sort of Karate Kid, wax on, wax off, okay? What we're really interested in now is we're going to start looking in earnest at how images are stored and the details of that. We're going to start first by considering black and white images just because they're simpler. The colored chips I gave you there demonstrate that color is a bit more complex. I'll talk about those tomorrow. I don't think we'll get to the colors you have there today. And let's imagine for now that we're interested in taking a black and white photograph and storing that in digital form. Okay? We use the word digital often synonymous with, quality, and that's incorrect. You can have a very poor digital representation of something. I mean, some YouTube videos are shocking bad. They're digital, but once something is in digital form, you can make perfect copies of it because it's represented in numbers and you can just copy the numbers. So that's sometimes how we confuse the term digital with quality. So let's say we have an image to digitize. The first thing we do is we break the image up into non-overlapping rectangles. These rectangles are typically squares, but they don't have to be. Okay? And then we look at each one closely. And for each area, we try to figure out how light or dark that is on average. So this area here is very light. This area here is very dark. This one here is probably, it looks to me like maybe 80 or 90% white and sort of 10 to 20% black. So maybe on average, it's maybe, 25% black or something. It's quite light on average. And then each of those values, or each of those samples, gets assigned to one of the quantization levels that we have. So the gray chips there you have on the table, for example, you could probably take one of these and figure out where along this range it fits in. And so we quantize the gray level of the image, of that portion of the image, and we give it one of the quantization levels. Now, for black and white images, 256 quantization levels are usually loads. There's plenty. And we can often make do with fewer. But in general, when you digitize a black and white image, it's 256 shades of gray, or 256 quantization levels. And it's 256 because we can do that in 8 bits. And that's convenient because bits are manufactured in boxes of 8 anyway. So the digital image then is made up of pixels, we call them. They're sometimes called pels, but I haven't heard that in a long time now. So pixel for picture element. And then each pixel's color is the same as the average color of the part of the image that it's standing for. So each pixel stands in for a portion of the image. And as we saw when we were measuring the temperature over time, we saw that there are 2 axes of quality there that you can deal with. There's the sampling rate, and there's the precision of the samples. And we'll see how that connects with images now. So the more pixels you have to store the image, the better the quality it's going to be. So if you have a lot of pixels, it's going to be nice and precise. If you have fewer pixels, not so much. Even in the metric parts of the world, we often still talk about dots per inch. So if you're scanning an A4 photograph in a scanner, you'd have the option to scan at maybe 800 dots per inch or 300 dots per inch. And depending on what you're doing, you'll have a different number of pixels then in your file. 300 dots per inch isn't great for something that's printed. It might be good enough to read text, but for a photograph it probably wouldn't be very good. 300 dots per inch is probably as low as you could go with your photos at the photo printing place in the pharmacy without it looking crap. 300 dots per inch for something that's going to be on the screen is probably plenty. It varies. If you take a picture on your phone and it's not a great phone and you get a huge poster printed up, it might not be great either. So depending on the context, you might need more pixels. But at the end of the day, you have a bunch of pixels and you can decide how many, when you're scanning first day, what kind of precision you're going to have, how many pixels you're going to have per inch, how many dots per inch, DPI. So this image here is 600 pixels by 400 pixels. Now by the time it makes it to your screen, it might be slightly different, but that's what we're looking at here. And that's pretty handy. 600 by 400 is fine. If I reduce that to 300 pixels by 200 pixels, which isn't half as many pixels, actually, it's a quarter. This image now has only a quarter of the information as the previous one. This is halved in both the X and Y axes. It's still kind of okay, I think. It's acceptable. If we half and half again, we'll be down to 150 pixels by 100 pixels. Now it's starting to get really ropey. Now, if you were actually standing out there at the number 8 bus stop, or the number 5 bus stop, well, if you were at the number 8 bus stop, you wouldn't see it. The number 5 bus stop, you might actually not notice that it's fairly crappy because you're so far away. But certainly even at the back of this room, this isn't great. And if we really push it out and go down to 75 by 50 pixels, you can see there that it's just not acceptable. So the number of pixels you have per unit of space is going to have an impact on the quality. And of course this is essentially the sampling rate. The number of times we look and see, okay, what's that? Okay, we'll assign that a quantization level. What's that? We'll assign that a quantization level. The number of times you take a look and see, that's the sampling rate. In addition to this, the more bits you use per pixel, the better the quality. So the more precise you store the sample, the better the quality of the image. So the more quantization levels you have, the more accurate the representation is going to be. So if I wanted to measure the height of everyone in the class, what I could do is I could get you to line up against the wall there, and I could count how many blocks tall you are. So I could say you're 6 blocks tall, you're 6 blocks tall, you're 7 blocks tall, you're 6 blocks tall, you're 8 blocks tall. And it would be a very rough approximation of everyone's height. If there was another room where we had like tiny bricks, then the range of values that would fit into each quantization level would be much smaller. There'd be many more ranges. There'd be more quantization levels. And so we might see more differences between your heights, and it would be a more precise measurement of everyone's height. So similarly, when we're saving the grayness of a pixel, when we're giving that a digital value, the more quantization levels we have, the better. So in this image here, it's using 8 bits per pixel or 256 different shades of grey. And like I said, for a black and white image, that's typically plenty. In fact, for this image, it's more than plenty. I don't think there are any pure white pixels in this image. And I think even the darkest parts aren't pure black. So I was going to show you it with 7 bits per pixel and 6 bits per pixel, but you couldn't even see the difference. So it went down to 5 bits per pixel. So in this image now, there are only 32 shades of grey. So each pixel is only one of 32 possible values. And I think it looks fine. If we go down to 4 bits per pixel, which is 16 different shades of grey, it still looks quite good. You can actually start to see it go, but you have to look really, really hard. If we go down to 8 different shades of grey, now you can actually see where it's starting to get a bit ropey. See, up here is where it starts to give first. Up there at the top of the central column, it starts to get a bit, we call that posterized. Now if I go back to the 5 bits and switch to the 4 bits, you'll actually start to see it now that you know to look for it. Can you see that? You can just about make it out. It's starting to give with the 4 bits per pixel. And so what's happening here is a bit like if you were measuring with the blocks on the wall. Even though, say, you and you are quite different in height, when you have few blocks, you both just get the same value. So as far as we're concerned, you and you are the same height. Where you have more blocks, you have more precision, and so you're not all then being thrown into the same quantization level. So when we go down to 2 bits per pixel, for example, there are only 4 quantization levels. There are only 4 shades of grey. And so every shade of grey in this image is forced to be just one of 4. So you look at it and you say, okay, it's like 20% grey, like it's 20% black. So, okay, 20%, you're in there with all the ones from 0 to 25. The next one might be, 47. Okay, well, you're in there with all the ones from 25 to 50. And so when that image then is displayed, all of the ones in the first quantization level, they might have the sort of 12% black. From 25 to 50 might be, 37% black. From 50 to 75 might be 67% black. And each pixel then is forced into one of those boxes, into one of those quantization levels. Where we have only 1 bit, obviously you don't get very far. We just have light and dark. But the important point here is that there are 2 dimensions of quality. There's the sample rate, which is the number of samples per unit of space or time, depending on what it is you're doing. And the more samples you have, the better. But you can also modify the precision of each sample. And as you change that, that has an impact on the quality as well. Any questions on any of that? Now I want us today to start thinking a bit about color and how color works. Because obviously most of the images we use are in color. And color is a bit more complex. In order to digitize something, in order to represent something numerically, we have to put numbers on it. And to put numbers on it, we have to put order on it. Now the black and white image, expressing levels of grey using numbers is fairly easy. Like we have a range of greyness. We have black at one end and white at the other. And then the shades of grey are in between. And really the only question is how many sections we have, how many quantization levels do we have? Do we have, 256 shades of grey? Do we have 16? But that's really the only question. It's fairly easy to put shades of grey in order. And that took you all a couple of seconds really to do that. Okay? So shades of grey, easy. Black at one end, white on the other. We can line up the shades of grey in between. But how do we put numbers on colour? That's a bit trickier. You know, like we know green isn't the same as blue, but like, is green more of something than blue? What's that something? I mean, green is more green, but you know, apart from that, how do we organize color? How do we put order on color? And I can see from the color chips on your tables that that's a bit of a struggle. It doesn't come as easily as the grayscale ones. Did anybody break out into kind of a two-dimensional grid? No? Sometimes people go into 2 dimensions. So that's difficult. So like if I brought you to my house and said, look, I had a whole wardrobe full of grey shirts, and I said, you know, like Ordnung was saying, you know, I want you to, you know, put them in order for me. Well, that's easy enough. If I gave you all my colour shirts and said, I want you to put them in order for me, you know, how does that work? It's trickier, okay? So how do we sort colour? How do we organise colour? How do we put numbers on colour? That's what we're going to try and address now in this class and in the next. So there are a number of different ways of looking at it. And the first way to look at it is using the hue, saturation, and brightness model, or HSB. So humans can see with their eyes a portion of the electromagnetic spectrum. I can't actually, I mean, I know it to be true when I believe it, but I can't actually get my head around the fact that the stuff that comes out of the 96 FM transmitter is the same stuff that's coming off, you know, my shirt and my shoes, and I can see. We think of light and we think of radio as 2 separate different things, but actually they're the same thing. They're just all part of the electromagnetic spectrum, and as humans we can sense a portion of that with our eyes. So we can see portions of the electromagnetic spectrum. Certain frequencies of that we can detect. Come back to the rainbow. So the portion of the electromagnetic spectrum from around 700 nanometers to 400 nanometers, that's what we can see that. Different species on this planet can maybe see different portions of that. Some species may see into the ultraviolet a bit, some may see a bit into the infrared a bit, some may see a lot less than us. Just like dogs can hear whistles that we can't hear, there may be things that different species can see that we can't see. If people came from another planet, well, of course they wouldn't be people, would they? But if aliens came from another planet, they might be able to see very different parts of it. But this gives us a way to organize color. The wavelength of the color is something we can use to organize it. So we could break up this like rainbow scale, for want of a better description, and say, well, depending on where you fit along the rainbow range, that's the value we'll put on your color. So we could break up color like this, and we could say, you know, from 700 to 710 nanometers you're in one section, from 711 to 720 you're in the next section, from 721 730 nanometers you're in the next section, whatever. Although by 730 you'd probably be invisible. But anyway. So that's a way we can organize color. So where a color fits on the rainbow scale is a way to organize it. So I could say, well, put all the reddish stuff at one end of your list of colors, put all the oranges and yellows next, then all the greens, and then all the blues. And maybe I could organize my shirts that way, perhaps. But it's not entirely satisfactory, is it? Now we call this the hue, okay? So where some color fits on the rainbow scale, that's the hue of the color. So is it red, is it orange, is it green, is it blue, is it indigo? But it's not enough. There's more going on than just the rainbow, isn't there? Like there's no pink in the rainbow, there's no white, there's no brown, there's no black, there's no grey. So there's more going on there. But certainly, you know, the rainbow scale, the wavelength or frequency of the color is a good place to start. We can agree that all of these shades here are sort of in the bluish area. They all have exactly the same hue, in fact, but they're quite different. These are all yellowish. They all have the same hue. These are all purpley. They all have the same hue, but they're not all the same color. So it turns out that color can be diluted. You can water it down. So if you imagine, say, a nice, hot, thick, dark, hot chocolate. You pour some milk into it and stir it around, it gets a bit paler. Pour some more milk in, stir it around, gets paler again. So you can dilute the color out of something. A really, really strong color has high saturation, and if you weaken the color, if you dilute it, then you've reduced the saturation. So we're going to have high saturation and low saturation. So like my laptop bag there that's orange, that's quite a heavily saturated orange, whereas this man's top is not heavily saturated in terms of color. Like it's kind of, that is in fact that's a red with very low saturation. That man up the back there, his green top is highly saturated green. Okay, so if color is really, really strong, it's got high saturation. That beige board over there, that green, is very highly saturated color. So if we look here, the green on the left is high saturation, but as we move right, the saturation is reduced. Now they're still all green. They still all have the same hue. In terms of red, orange, green, blue, indigo, violet, you know, they're still green. And they're all the same hue, but it's the saturation is reduced as we go across. So we have hue and we have saturation. We have the color and then we have the strength of the color. We're nearly there, but we're not quite. Okay? So here we've got different saturation levels of green, but there's more going on. So look, if we look at these shades of yellow here, we have hue and we have saturation. These all have the same hue and the same saturation. There's one more thing going on, and that's brightness. Now, luckily though, we're on familiar territory here. Brightness is just a measure of how bright something is, how much light is coming off of it. And that's not unlike what we considered when we looked at black and white images. So if I gave you colors that all had the same hue and all had the same saturation, organizing them by brightness would actually be as easy as the grey ones you had there. So if I had printed the grey color chips on colored paper, of course they wouldn't be grey, they might be, you know, pink, but you'd be able to organize them because they'd have the same hue and same saturation, and the brightness would be easy to organize. So imagine you are nostalgic for the 90s or something, and you want a colored light in your bedroom. and you might decide for reasons best known to yourself you want it to be in red. You might go into, say, B and Q, and they might have all these light bulbs organized by hue. So there might be like red ones there, orange ones there, yellow ones, green, blue, indigo, and violet, okay? Inside in the red section then, you might find that there's like really vibrant red ones, and there's sort of pinky red ones. You might decide to go for the heavily saturated red one. So you've gone for hue, red, and saturation, high. Okay? So you bring it home, plug it in, and now you've got a dimmer switch on the wall. When you turn it up fully, you've got your hue is red, your saturation is very high, and your brightness is very high. As you turn the dimmer switch down, you're starting to reduce the brightness, so it gets darker and darker. It's still red, it's still saturated red, but it's getting darker. And eventually you turn off the light and it's black. Can't see a thing. So you have hue, saturation, and brightness. And with those three things, you can specify a color. But you need all three things. So if you were to organize my shirts, you would need not only a rack that goes from left to right, okay? You might then need several stacked on top of that for the different saturation levels. And then you'd have to go back into a third dimension to organize the brightness. So at the front you'd have the bright ones, at the back you'd have the dark ones, at the bottom you might have the heavily saturated, and as you go up you might have the lower saturated. So it needs to be done in 3 dimensions. But most of you didn't even try and break out of the 1 dimension there. Now, hue is typically expressed as a point on a wheel, on the circumference of a wheel. So it's like how many degrees around you've gone. The saturation is usually expressed as a percentage, 100 to 0, whereas high would be 100, heavily saturated, 0 would be no color in there at all, and then brightness again from 100% to 0. 100% would be light, 0% black. Most operating systems have some form of a color picker that you can use to select colors. So you could go into PowerPoint, for example, and just decide to put something there and pick a color. What I'm going to do is I'm going to show you the wheel first. So so here's the wheel, and this here I think this is the starting point, and it goes around like this. So here would be this would be a few degrees. It doesn't actually show us the values there now. So that's 7 degrees, okay? As we go up here, we'll be up to kind of like 90 degrees. Would be green. Let me just see if that's correct. Yeah, 90-ish. Here then we'd be at a 180 degrees-ish. Come on. Would you come on? Here we go. So as we go around the circumference of the color wheel, we're changing the hue. And you see there we're cycling through kind of the rainbow scale: red, orange, yellow, green, blue, indigo, and violet. So hue is expressed as the number of degrees going around that wheel. The saturation then is basically a question of how far in you are from the edge. So here, as we get closer to the center, the saturation is reduced. So not to pick on him, but he did sit up the front. So his top there is red, is the hue, but the saturation is turned down So we get that sort of, I suppose, a pink, you know, nothing wrong with wearing pink. That pink color there. And we can specify the brightness then here. But this is actually quite a bright shirt he has. So the brightness is high there. So we can specify the color of his shirt in terms of hue, saturation, and brightness. What about that man up there with the green one? The hue is green. Anybody want to speculate how many degrees that might be? It's about 90, wasn't it? Up here somewhere is around 90. In terms of saturation, high saturation or low saturation? High, let's face it, it's up there. And brightness, you know, it's fairly bright as well. So hue, saturation, and brightness gives you a way to store color numerically. Okay? You can get sliders as well. You just slide them across and see the values. Now, the system we're most interested in, though, is the RGB system. And that's not as natural. It's a bit harder to talk about. But it's the system that's used in most computer systems. So with the RGB system, you may remember seeing this in physics class, where you have a red light, a green light, and a blue light, and where you shine them together. Where the red and the green and the blue mix, it's white. Where the red and the green mix, you get yellow. And where the red and the blue mix, you get magenta. So for each color, we talk about how much red it has in it, how much green it has in it, and how much blue it has in it. RGB, red, green, and blue. And we use 256 quantization levels for each of those. So it's 1 byte for each of those. So you have 3 bytes per pixel. So to represent the color, we use 3 bytes. So you sometimes hear or see things saying 24-bit color. Back when phones were crap, they would boast about how many colors they had. And so 24-bit color is using RGB. In the past, they didn't use 8 bits for each color. You might have used only 6 bits for the red, 6 bits for the green, and 6 bits for the blue, or even less. RGB gives you up to 16 million and however many colors. Which is considerably more than we might need, which is something we'll come to in the next class. So here, in this shade of red, the red is turned up fully. 255 is full red. The green isn't there at all, and the blue isn't there at all. So we know that only red is at work here. And because it's 255, we know it's cranked up to the max. So this is pure red. Here, there's no red, there's no green, and it's only blue is at work. So we know it's going to be some kind of blue. 200 is pretty high up there. I mean, it's almost up to 255, not quite, but it's still pretty much up that end of the scale. So we can see there's quite a bright blue. Now the RGB system is additive, not subtractive. So the more values, the higher the values, the brighter it gets. So high numbers is bright, low numbers is dark. Here the red is cranked up fully, the green is cranked up fully, and the blue isn't there at all. So it's pure yellow. Here there's no red and there's no blue, and the green is quite high. So it's quite bright still. Here no red and no blue, and the green is the only one at work, so we know it's green. But you see that the value is lower than it was before, so the green is darker. When the red and the green and the blue values are equal, you get a shade of grey. Here, they're equal and they're quite high. 200 is up there. So we can see it's quite a light shade of grey. Again, here the red values, the green values, and the blue values are the same. But they're lower, so it's darker. Here again, red, green, blue, all equal, but it's lower again, so it's darker again. The red and the green and the blue are cranked up fully. It's a shade of grey, but it's white. It's so high up, it's white. And needless to say, 0, 0, 0 is black. So no green, no blue, nothing. So you're in a room, there's a red light, a green light, and a blue light, and they're all turned off. Well, yeah, it's black. No. You may have seen this in HTML, or you may have not, but when you're specifying your colors in a CSS style sheet, you can specify the color using the RGB values. And you can say RGB open bracket 128, 128, 255, or you can use a hexadecimal codes there. I know some of you are quite comfortable dealing with hexadecimal, and some of you not so much. Looking at the shade of blue here, the red value is 128, the green value is 128, and the blue value is 255. 128 in hexadecimal is 80. So we get hash 8080 FF. 255 is FF. So although it's possible to specify the color in decimal, typically it gets expressed in hexadecimal just because it's very convenient. It's 6 digits, 2 for each color. So each pixel then in the image has a red value, a green value, and a blue value. Sometimes it's instructive to see the image just in the red channel, or just in the blue channel, or just in the green channel. Sometimes that can be informative. So when you're in the red channel, for example, and you can do this in Photoshop, it might be worth a look when you're in the labs next. The red value of the color red is very high. And the red value of white pixels is also high. So in the red channel, it can be quite hard to distinguish between white pixels and red pixels, for example. And we see that here, that it's hard to make out the difference between the red ones and the white ones. So here in the red channel, this time they're visualized as grayscale images, one for red, one for green, one for blue. And inside in Photoshop, you can edit just the blue part or just the green part if you want. So here, it's hard to see the difference between the red and white stripes, whereas in the blue and the green channels, it's not so bad. Imagine my delight when I saw 3 doors lined up, red, green, and blue. Not that far from here either. So in the red channel, the red door is the lightest. In the green channel, you see that the green door is the brighter. And in the blue channel, the blue door is the one with the most blue. Although there's not a whole lot of difference between the green and the blue. Looking at this here, we have FF00. So the red and the green are cranked up fully, and there's no blue. So you can see that it's bright yellow. So up the back there, what do you think this one might be? FF2020. I haven't picked a new one off today now already yet. So here is the red value is the first 2 digits, right? And is that high or low? High. It's at maximum. So this is at maximum red here. Okay? And the green and the blue are the same. Are they high or low?
Low.
They're quite low. They're almost not worth talking about. So in this color here, it's mostly red. We've got full on red, and then there's a bit of green and blue that aren't worth talking about. So what color do you think it is going to be? Red. It's going to be red. Okay. Next up there, what do you think this might be? No, next. You need next. So the red is just not there at all. There's no red, no green. So it's only blue.
Dark blue.
Yeah, and why is it dark blue? The blue isn't turned up fully, like. It's kind of about halfway. So we're confident it's blue. The only question is how bright it is. That's dark enough, yeah. Next up there, what do you think this might be? You're next, yeah. What do you think it might be? No, the man next to you. So the red is high, isn't it? Well, what's the dominant color? Remember, the first two are red, the first two are green, the next two is blue. Blue. So blue is the most prominent color here. Now, are the red and the green values, are they high or low? They're quite high. They're quite high, in fact. Let's tackle this a different way. If it was D0, 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 what would we have? Grey. And would it be a light grey or a dark grey? Be quite a light grey. So let's consider this to be a light grey where the blue has sneaked ahead a bit. So it was grey, and then the blue made a run for the finish line. It was a light grey with, blue tendencies. So I think we're looking at a light blue. Okay? I see some heads being wrecked. No. What about this one here? 808080. It's a shade of grey. Light or dark or in between? Remember now, it's base 16. So 8 isn't nearly at the top. 8 is like exactly halfway. So 80, 80, 80 is like kind of 50% black. So it's a kind of in-between grey. Here we have E0, 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 which is a light shade of grey. So what might this be? FF E0, E0. Man at the edge of the seat there. What do you think this might be? No, you there. What do you think this might be? Bear in mind now that E0, E0, E0 is that very light grey. So if we had a light grey and the red made a boat for the finish line at the last, what might we end up with? So we have a light grey, very bright grey, and then there's a bit of red thrown in at the last minute. It would be pink. See, I made him sit here at the front today with that colour shirt. So if you have a light grey and then you throw in a little bit of red at the end, you're going to get this pink. So this is the colour system that most computer systems use. And as you can see, it's not as natural as the HSB really. If I was to say to you, is this kind of reddish, greenish, orangish, yellowish, greenish, or bluish, or purplish, you'd quite happily fit your colours into there. If I said to you, is this a strong colour or a weak colour? Is the saturation high or low? You could very naturally give an answer, and lightness and darkness is trivial. Looking at a colour, how much green is in that, how much red is in that, how much blue is in that, it's not as natural, I don't think. but it's the system that computer systems use. So you need to understand it. Any questions on that? So the next class we'll look at some other color systems.